Okay, so for lecture number 11, problem 1. The idea here is that we have a sphere, okay? And we'll say that that sphere is a volume of charge, okay? And it has a uniform volume charge density of rho sub v, right? That's rho sub v coulombs per cubic meter, right? You take any little cube out of there, any volumetric cube, and I can tell you how many coulombs are in that volumetric cube. Okay, so we want to use Gauss's law to determine what the formula is for the electric field intensity everywhere, okay? So, again, this is a Gauss's law problem. Let's write down Gauss's law. We say the net outward flux will be equal to whatever the charge enclosed is, okay? So this problem ends up being a little more complicated. This is similar to the coaxial cable problem I showed in class, where you have to break this up into two components because the enclosed charge is going to be different whether we're inside the sphere or outside the sphere. Because as you can imagine, when we're inside the sphere, depending on how far we are from the center of the sphere, there's going to be more charge enclosed, and it'll keep adding up until we get to the boundary of the sphere. When we get outside of the sphere, we can say basically out here the volume charge density is equal to 0, right? So no matter how far away we are outside of the sphere, we only enclose the charge that's enclosed inside the sphere, okay? So we're going to have two Gaussian surfaces. So if we take a cross section of this, so here's the sphere, right? That's the sphere right there. We need to have two different Gaussian surfaces because we have two different charge densities, right? So inside here will be our first one. We'll call that GS1, right? And outside here, we're going to have our second one is GS2, okay? So inside GS1, we have rho sub v is equal to some uniform value of coulombs per meter, and outside here we have that rho sub v is equal to 0, right? But whenever we enclose this here, we're enclosing all the charge that's in the sphere plus 0 what's outside of the sphere. So we need two different Gaussian surfaces. Okay, so as always, we do the left-hand side, and we only have to do this once. Well, we know from a sphere, like a point charge, that the flux lines are going to be directed radially outwards, right? So we can say that, based on intuition, we know that D is going to be, it's going to be directed in the R direction, okay? And then it's also going to be only a function of R, right? Because regardless of where we are in the theta direction, in the phi direction, it's going to be the same. It only gets weaker and weaker the further away we get from it, okay? And that's going to be in that AR direction, okay? So we get dr. Now, if we're going to pick a sphere as our Gaussian surface, well, we have to know what ds is, okay? ds for a sphere is going to be equal to r squared sine theta d theta d phi, right? So whenever we calculate d dot ds, we can see that we're going to get dr r squared sine theta d theta d phi, okay? And then what are our bounds? Well, theta for a sphere goes from 0 to pi. Phi for a sphere goes from 0 to 2 pi, okay? Now, the question is, can we say that the dr component is constant when we're evaluating this? Well, yeah, we can actually, because if you think about this, for a sphere that we create, we're saying that sphere is at some radius r, and anywhere on that sphere the radius is always equal to r, so it's a constant r value. So r is constant and dr is constant. We can just pull those two out. dr times r squared, 0 to 2 pi, 0 to pi sine theta d theta d phi, okay? And calculating that before, remember I showed you that the integral of sine theta from 0 to pi is going to be equal to 2, and then we have 2 pi, so we're going to get 4 pi r squared dr, okay? That's the left-hand side. All right, now we have to handle the right-hand side. The right-hand side is handled differently depending on where GS1 or GS2. So for GS1, we'll say we're inside the sphere. Let's say the sphere has radius A. Okay, so that means R is less than A, right? So R is less than A. We have to find out what is the Q enclosed. Okay, well that depends, right? That depends on how far out we are, right? And it's an arbitrary value because we're trying to solve for E everywhere. So we're going to say, where are we? Well, we're at any arbitrary distance R away from the center, okay? So our bound on R is going to go from 0 to this arbitrary value of R. Our bound on theta is going to be 0 to pi and 0 to 2 pi for phi. Okay, now we have rho sub v times dv, which is going to be r squared sine theta dr d theta d phi. Okay, but notice again, we can't integrate to r if r is in our integral, right? That wouldn't make sense. So let's put a prime here so that we can call this r a dummy variable, just a dummy variable integration. Okay, so when we do that, we can see again that where we integrate sine, we're going to get 2. We integrate d phi, we're going to get 2 pi, right? So what we're going to get here is 4 pi rho v divided by r cubed all over 3, right? And then we can set the left and right hand side equal to each other. And we can say that 4 pi r squared dr is equal to 4 pi rho v r cubed over 3, right? And we can see that the 4 pi cancels out here, the 4 pi cancels out here, this r squared cancels out 2 of these, so we're just left with r here, and this says that dr then is equal to rho sub v times r divided by 3, okay? And then we can obviously say E is simply equal to rho sub v times r divided by 3 epsilon naught, and that's directed in the AR direction, okay? This is only for the bounds when r is less than A, right? So r goes from 0 to A. This is our equation for the electric field intensity. And we can see the further away we get from the center, the field starts strengthening because we're enclosing more and more charge, okay? Now, when we go to the next one, we have Gaussian surface 2, which says that R is, oh, sorry, not rho, but rather it should be R. So R is greater than A, okay? R is greater than A. Well, look, all we have to do is evaluate for the Q enclosed, okay? So for this point, we're saying that R is somewhere out here, right? We have to calculate all the charge enclosed, right? But we don't have to go from 0 to R because anytime R is greater than A, we're enclosing no more charge. So it doesn't matter how far out R goes, we only enclose the charge inside the sphere, okay? So that means the boundary on R is only going to go from 0 to A because beyond A, we enclose no more charge. Theta 0 to pi, phi 0 to 2 pi, and then again we're going to have the same equation. Rho sub v r squared sine theta dr d theta d phi. This time we don't need the dummy variable because we're not integrating to an arbitrary r, we're just integrating to some finite value a. So when we do this integral, again we're going to get the same thing. 4 times pi times rho sub v, except instead of having r, we're going to have a cubed over 3. Okay, setting the left-hand side and the right-hand side equal to each other, we get 4 pi r squared dr, and we set that equal to 4 pi rho sub v a cubed over 3. These 4 pi's cancel out. This time we'll see that the r squared does not cancel out, right? It's going to divide to the other side. So we'll say that dr is equal to rho sub v a cubed divided by 3 times r cubed, r squared rather. Okay? So now you can see since a is constant, when we start getting outside of there, it's going to start decreasing because you can see the flux is inversely proportional to the distance away from the center, right? So as we expected, it's going to increase while we're inside the sphere. Then when we go beyond the sphere, it's going to start to decrease, okay? So then E would be equal to rho sub b a cubed divided by 3 epsilon naught r squared, and that's in the AR direction. Okay? So we can now say, what is E? E is equal to two different things depending on where we're at. When we're inside the sphere, rho sub b times r divided by 3 epsilon naught AR. Okay? And that's when r is, let's say, less than or equal to a. It's going to be continuous, so we can say less than or equal as long as we don't say it on the next one. And then we'll say, okay, that's good. What is it when we get beyond, what is it whenever we get beyond there? And we can say rho sub b times a cubed divided by 2 epsilon naught r squared AR. And actually, we can say that that's when r is greater or equal to a. And why can we put equal to a there and equal to a there? Well, the reason being is because this is a continuous function. So you can actually plug in the value of a there and plug in the value of a there, and you should see that you get the exact same answer. So it doesn't matter. This doesn't violate our equation, right? So let's look at what does that look like as we plot this as a function of, so this is the electric field intensity, and this is the distance away from the center of the sphere. Okay, so what happens? Well, here you can see we have a linear increase until we get to some point. That point is going to be A. We get a linear increase at some point equal to A. What is that actual value? Well, that actual value, just put in A, and it's going to be rho sub b times A divided by, 3 epsilon naught. 3 epsilon naught. Okay, that's going to be its maximum value. Then it begins to decrease, right? And it's going to decrease like this. Right, and the further away we get, the closer it's going to go, until we get so far away that at some point it's completely negligible and we can't observe any field at some point away. Okay, thank you.